All right, sorry I'm late by 2 minutes, but we start, I suppose. I want us to make it quick because I'm rushing for another meeting, and so it's going to be probably one of those relatively short classes. But anyways, I just wanted to find out if people have questions related to what we looked at. Was that day before yesterday or something? So we started so-called binary multiplication. And we just really walked through a few examples of how we go about multiplying two binary numbers. And I think we parted ways by, before we part ways, we looked at a very strange example where you're multiplying relatively large binary numbers that will result in those intermediate outputs that might need to be broken up into separate components for you to be able to apply those binary addition rules. Because remember that fundamentally, when we're multiplying, at some stage we get to employ binary addition, right? So hopefully that made sense. And so we continue our conversation from where we left off, which is transition immediately to binary division. All right. Good stuff. Good stuff. Okay, so it turns out that binary division is quite trivial if you decide to take advantage of the long division method that was introduced to us in grade 1, right? I don't know if you still remember that, but if you don't worry. Fear not, we shall revise it. It'll be a quick revision, right? So we take advantage of long division, and the concept is the same. So you try and ascertain how many times the divisor goes into the quotient, and then you keep track of the remainder and the result, right? And then you apply, obviously, subtraction, right? So we're going to take advantage of the same approach here, right? And what I'm referring to here is, I don't know if this is the same thing here. Beautiful. So if you remember from grade 1 here, if you're dividing, let's say 34 by 2, and remember, the cases that we're going to work on here are perfect integers. We're not dealing with double floating point values here. It's just plain integers, right? Which is why we're very careful about the numbers that we're working with here. The end result will always be an integer, right? A whole number, in other words. So just a reminder here, applying long division to 34 divided by 2, you first of all divide 3 by 2, right? The answer is 1, and then you multiply 1 by 2, you keep track of the result, which is 2, and then you subtract 2 from 3, you get 1, right? Sorry, I should have put a minus sign here, I guess, I don't know. So what we're saying is you subtract 2 from 3, you subtract 2 from 3, keep track of the number, and then you drop down 4 there, right? Because 2 can go into 1 here. You have 14, you divide 14 by 2, you're going to get 7, you multiply 7 by 2, you get 14, and then you subtract. You stop once you converge, right? And you converge once you get an answer of 0. And then you get an answer of 17. 2 times 17 obviously gives you 34. You remember this, right, from primary school? Yeah?
Yes, sir.
Yeah, I remember this as well. Mrs. Mazwanga taught me this myself. All right. I wonder if she's still alive. She's relatively old at the time, but God bless her soul. So here's the thing, right? What if we have these two numbers here? We want to divide 1010 with 101, right? So effectively what we're saying is since 1's place, 2's place, 1's place, 2's place, 4's place, 8's place, a plus 2, that's 10. We're dividing 10 by 1's place, 2's place, 4's place, 4 plus 1 is 5. So we're dividing 10 by 5. We want to get 2, essentially, right? I do apologize for the color coding here. This was supposed to have been completely transparent. You aren't supposed to see these numbers, but that's fine. We can change it later on. So long division, right? We have the divisor, right? Here. right? And then we'll have the quotient. Oops, sorry, we have the quotient here, right? All right, so same process, we start by checking. How many times does 101 go into 1? And the way you do this, right, is you have to think about this. And I know it can be hard because you're still not used to base 2 here. But one way of checking whether a number you're dividing into is small or greater is by looking at the digits, right? So in this case, we're dividing 101 into 1. We know that 1 is obviously less than 101, right? 1 is 1. I mean, this has additional digits aside from 1. It should be 1 plus 4, right? Which is like 5 or something. So 1 into 1 is 0, right? We come here, 101 into 10 is still going to be 0 because 10 is less than 101, right? So it's still going to be 0. And then we have 101 into 101. We know it goes there 1 time, right? 1 times 101, we're going to get 101. And then we subtract 101 from 101, we get 0. We drop down the 0. We divide 101 into 0. We get a 0. 0 times that, we get a 0, and then we convey. So the answer is 10 or 0010. Right?
Sir.
Wondering why this is. Yes, sir.
Yes. How about in instances where if dividing with the first number leaves a remainder, where do you put the remainder?
What do you mean dividing number leaves a remainder? As in?
Let's say, no, the previous example before this one.
Yeah, this is the previous example.
No,
I mean this?
Yes, that one. It's a 2 into 3. No, before this one.
There's nothing before this.
Yes, this one.
Okay.
Yeah, here. What I mean is 2 into 3. Isn't it like 1 remainder 1?
Yeah, but you're just keeping track of the whole number, right? So we're saying what we're saying here is we're saying 2 into 3 is 1, right? You only care about the remainder once you subtract. 1 times 2, you keep track of the whole part, right? How many times does 2 completely go into 3? It's 1 time. Forget about the remainder. 1 times 2 is 2. And then you evaluate the remainder. You essentially, you successively or repeatedly divide by keeping track of the remainder, right? So the remainder is here, 1. This thing here.
Right, sir.
Yeah. So here's the thing: if you've forgotten long division and you have a younger sibling who is still in primary school, trick him or her into teaching you. Just don't tell her that teach me division, but just try and pretend like you are trying to teach that person. Right? Can you show me how to divide? How do you divide or something? Just to remind yourself. Anyway, so here's the thing, right? Another example here. I'm very careful with the time here. It's simple stuff. Another example here, what if we divide, and I do apologize here, there's a bit of a mistake again. This is supposed to be 1, 0, 0, right? There's 2, right? And then this is supposed to be 1, I think so, 1, 1, 0, 1. 0, 0, right? Actually, 3 zeros. So effectively, what we're saying here is we are wanting to divide 0, 0. We are wanting to divide. Forget about this. I'll change the slides here. If you notice, this is the same as the question that was before here. But we are wanting to divide. This is 1's place, 2's place, 4's place. This is 4. 1's place, 2's place, 4's place. 8th place. I guess this is now a good time to just calculate this instead of doing this. So we are wanting to evaluate 1, 1, 1, 0, 1, 1, 2, 3. So we are dividing 232 by 100, right, which is 4. So we expect the answer to be 232 divided by 4. 58 is what we're aiming for, right? And in fact, we know that once we evaluate this 1101000 divided by 100 should be able to give us this number here. I guess it's 26. Okay, 26. 26. Let's see. 110123 in decimal. Oh, okay. 110130. Okay, so it's 104. 104 divided by 100 by 4. So it was supposed to be 104 divided by 4. Beautiful. So 26. So we want to get 26, right? In fact, we were dividing this. So same process. We first of all start by checking. 100 into 1 is 0, obviously, right? Because this is much, much smaller, right? 100 into 11 is still going to be 0, right? Because 11 is smaller than 100. 100 into 110 obviously is going to be 1 time because this number here is smaller than this number, right? And then we multiply 1 times 100, we get 100. We then subtract 100 from 110, right? Observe, same process. And I was kind of hoping that would, I was hoping that we'll get into a situation where when we are subtracting, the only trick here, right, when we're going through this process, the only trick is instances where your subtraction process as you are dividing involves you borrowing from adjacent twos places, right? Unfortunately, there isn't really an example that that manifests itself that way, but that's besides the point. The same process here is we are subtracting here. When we're subtracting, go through the same process. 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 1, right? And then we have 0, 1, 1, 0. Right? Because this is much smaller, we have to we have that. Because this is much smaller, we drop 1, right? And then we divide 101 by 100, we get 1. We multiply 1 by 100, we get, sorry, by 100, we get 100. We subtract 100 from 101. I was kind of hoping we'd get into that situation anyway. And then we subtract, we get 1 here. We drop down the 0. Yeah. Once we drop down the 0, we divide 10 by 100, we get 0, right? We are going to have to drop the other 0, right? Because this is much smaller. If you want, you could have just said we multiply 0 times 100, in which case would be 100 and we subtract something, but we drop down the 0. And then 100 into 100, we will get 1. We multiply 1 by 100, we get 100. We subtract 100 from 100, we get 0. We drop down the remaining 0 here, right? Once you drop it here, we divide this into 0, we just get 0, and then we converge, right? The answer is 11010, right? Which should be 26 actually. So the only thing here that I want, the part I want to draw attention to here is the part where you are repeatedly subtracting, right? Because it turns out that as you are going through this process here, the subtraction process, like when we came, all of these sub-processes that we have here, this part here, the subtraction rules we looked at apply, right, in all these different instances. Right. All right. If there are no questions, I mean, this is trivial stuff. If there are no questions, I would like for us to proceed and start talking about signed and unsigned integers. Right. I think we still have a bit of time, unless if there are questions. Is there any part that is confusing for you?
On the subtraction part there, on the part where you have highlighted in red, the situation you're talking about, what if we have a situation where we have on top we have 0, 0, 0, then down we have 1, 0, 0, then want to subtract 0 from 1, we know that we have to borrow from somewhere. Can we have that situation? Which
Which part are you referring to?
Pardon?
Which part are you referring to? You're saying, could you repeat?
The same one which you have, the same one you have highlighted there in red. Assuming that the top part was, assuming that the top part was 000, and then the bottom part was the same 100, and then we are subtracting. Oh yes.
No, I mean, so if you're subtracting, right? What you do is, if the number is less, you start dropping down the numbers here. You only get to, you only get to subtract once you. So let's just double back here so that you understand what's happening. I hope it works here. So I guess when you come here. So you only get to a stage where you are, in fact, the instances where you subtract are only going to be when the number is either, the number on top is going to be either greater or equal to the number that's going to be below. I don't know if you've noticed this. If you keep track of, sorry?
Maybe I can try to explain. What he's saying is, for example, if the number on top is 101 and then the number at the bottom is 10.
Yeah.
Yes, you have to borrow a digit from the first one so that the 0 at the top can subtract the 1 at the bottom. So what can you do in that case?
No, so this is what I'm saying. These different instances, you can only have a situation. Observe this, and I'm just going to go straight until the end, right? If you look at, if you look at all these numbers we've been subtracting, right? So observe. I don't know if you can see the pattern here. This bit, this bit, and this bit. In fact, we can double back to the previous example, and what you will notice is that in all of these cases, the number on top is always greater or equal to the number below. So the borrowing part can be done if you have a situation, let's say, and I'm trying to think of a scenario where the number below might be, it might be larger, but then it might have a digit where you would have to 1011. No, so yeah, I can't think of a scenario right now. So, but if you look at this part here, right, the borrowing might take place. I don't know, maybe not. But the key thing to notice here is that the number that you have on top, 110 against 100, is always larger or equal to 101 against 100, 100 against 100. If you double back here, you notice that there's a similar pattern here as well. Let's converge. 101 against 101, which is the same, I guess. Right? I don't know if there's something else here, probably not. But I don't know if that answers your question. And in fact, it's the same rule applies to long division using base 10, right? The number on top, when you're dividing, it's always greater. I don't know if I've answered your question, but
oh, yeah, yes.
Yeah, I don't know. All right. So on with it then. So we're going to just start our discussion of so-called unsigned integers. Up to this point, our conversation has been centered around unsigned integers, right? But we want to set the stage to have a discussion of signed integers, right? Because it turns out that a computer will generally work on both positive numbers and negative numbers, right? So, so by unsigned integers, we simply mean, you can just think of them as being positive numbers, right? So from 0 up to infinity or something, right? And you typically increase these numbers by 1 bit if you're looking at binary numbers, right? On the other hand, to think of, okay. Okay, so in terms of the representation of these numbers, obviously we have highlighted the fact that we can derive the equivalent byte associated with bits, right? So up to this point, we've been saying that 1 byte is the equivalent of 8 bits. And so we can pretty much determine the total number of integers that can be represented by these bits, right? So what we're saying here is we're saying it's 0 through to 255, right? All you have to do is just work with powers of 2, right? So 0 through to 2 to power 0, 2 to power 1, all the way up to 2 to power 8 minus 1. Right, this is in the case where you have a byte, right? But if you have a number that's being represented, let's say using 16-bit representation, you notice that there's a similar pattern. What you have is a situation where you're representing numbers from 0 all the way up to 16 to power the bit representation minus 1, right? If you're working with a 2-bit representation of a number, which is usually the case for most processors, like the simulator that we're going to be working with very, very soon, what you're looking at doing is representing numbers from 0 all the way up to 2 to the power 32 minus 1, right? Now this is really interesting because it raises interesting questions regarding how many numbers you can represent, right? Given a certain bit representation. You notice that if you're working with positive numbers exclusive, what we're saying is we can only represent these integers 0 up to 4,294,967,296, right? Anything beyond this, we cannot represent, right? If you're working with 16-bit representation, we're saying the maximum number or the maximum integer we can work with is 65. Now, this, by the way, will come up again when we start looking at the MIPS, this is 306, MIPS assembler. You'll notice that you might find yourself running into these sort of problems here, right? I don't know if you can see this, but you run into these sort of errors where if a number that you're trying to slot into, let's say a register that can only hold 16 bits, for instance, goes beyond the maximum threshold, then you get an error, right? Because it can't hold, the value that can be held in that register cannot go beyond a certain threshold. Right? So I'll put it out there here. Right. So this is for unsigned integers or positive integers. An interesting question to ask though is how then, given that at this point in time we've figured out exactly how positive numbers behave, how we can represent them, how then can we store and encode signed integers, right? How can we efficiently store them? And even more importantly, how then do we perform operations we've been performing so far, like subtraction, if we have a negative number, if we're working with a negative number? It turns out that smart people have come up with different methods of doing this. And traditionally, the most common methods that are discussed in literature is so-called sign magnitude, 1's complement, and 2's complement. So our conversation going forward is going to be centered around these different methods. We would like to, and I would like you to pay particular attention to the disadvantages of certain techniques here when you're representing negative numbers. I guess I'll give it away here, but you notice things like misrepresentation of certain equivalent decimal numbers, for instance. In certain instances, you'll find that if you use a certain technique, you have situations where you have a negative 0 and a positive 0, something that doesn't make sense. I mean, you could putatively say it does make sense to us, but the problem is you're wasting space, right? It doesn't make sense that you have a negative 0 and a positive 0, for instance. Some other things that you will see manifest as we are looking at these different methods is that when you're subtracting certain numbers, the result that you get back does not make sense, right? So for instance, when you try and subtract a positive number and negative, certain positive numbers and negative numbers using sign magnitude, you realize that you get an answer that makes absolutely no sense, right? So I would like for us to pay particular attention to these things as we are discussing this. So we'll start with sign magnitude, right? So the idea behind sign magnitude here, and it's in the name signed or sign magnitude, is that you use one of the bits, right, in the binary number to represent the sign, right? So whether the number is going to be positive or negative. And then the remaining bits are used to represent the size of the value, which is the magnitude, right? So you have the sign and the magnitude. And conventionally, a 0 represents a positive number, and a 1 represents a negative number, right? So if you're representing a binary number using sign magnitude, when the leftmost bit is a 0, then you know that that number is a positive number. If the leftmost bit, or the most significant bit as they call it, is a 1, then you know that that number is supposed to be a negative number. So notice this slide here, what we're saying is that to represent -5, would represent it like so, where this value here tells us it signals the fact that the number we are representing is a negative number, right? The remaining part is what you convert into the magnitude or the value of whatever it is you're storing. Yeah, right. So that would be your sign, and the remaining bits on the right would be the magnitude. Yes.
Do you mind going over that again? Where the last number is negative or positive? I missed the part there.
Yeah, well, so what we're saying is that sign magnitude is simple, right? It's for you to represent, when you're representing a number using sign magnitude, we're saying you do two things. You use the most significant bit to represent, let's look at an example like 10, for instance. Oh, I guess 10 is fine. Let's look at -10 and -10 and +10, right? We know that in binary, 10 is nothing more than 8 plus 2, right? Yeah, 8 plus 2. So ones place, yes, we just start it here. Ones place, twos place, fours place, eights place, right? So this is our 10, right? Forget about the sign for now. This is 10. Assuming we want to represent -10 in using sign magnitude as well, first thing we do is we just compute the magnitude, the size of 10 base or -10 base 10 into binary, right? Forget about the sign. And then conventionally, as the final step, the most significant bit or the leftmost bit is supposed to encode the sign, right? The magnitude for these two numbers is going to be the same. The thing that sets them apart is going to be, the thing that's going to set them apart is going to be the bit that tells us whether it's a positive or negative. And we are saying conventionally, a 0 tells us that the number is a positive, a 1 tells us that the number is a negative, right? So this would be your +10, this would be your -10 using sign magnitude. So essentially, the leftmost bit or the most significant bit represents the sign, and the remaining bits will represent the magnitude or the value of the number you're representing. Yes.
So
yes.
Would it be alright to represent a positive, like, without putting a 0 there? Like,
Would it be what?
Would it be alright not to write a 0 there, since you know that it's a positive, so you don't write anything there?
Well, so it depends on. It would be all right. Yes, it would be all right. I mean, you could assume that it is a 0. But again, it also depends on whether you are being explicitly told the bit representation that's being used, right? In this case, and the bit representation is important, because you'll notice very, very soon that for these other techniques, when you have an overflow, you almost always have to make a decision on what you're going to do with the overflow bit, right? And it will make sense very, very soon. But yes, you can. It would be okay for you to omit it, because you just assume that. I guess it's tricky though, right? Because removing it would make sense if you've been told the bit representation. But if you haven't been told, if you think about this for a second, right? If I ask you a question to say, look at this is 10, right? I come to you and I ask you to say, tell me, what number, is this a positive number or a negative? Is this a positive number using sign magnitude? Is 1010 positive or negative? That's a question. Oh, it's a question. I'm asking a question.
I think it's negative, sir.
Yes, thank you very much. This is a negative number, right? Yeah. But if I tell you what, using sign magnitude, is this number negative or positive?
Positive.
Exactly, right? So I guess I've answered your question somehow, right? You want to be very careful here. Very, very careful depending on the technique that you're using. Yes.
So it's positive if the last number is 1, and then it's
Not the
negative
last,
when
not the
last
last
most number is 0.
No, the most significant bit. The last number here is, you don't want to confuse yourself. I don't know what last is here. The last is here, right? I don't know where last is. My last is on the right, but I don't know. But let's stick with the stuff we're talking about. The most significant bit. If the most significant bit is 0, the number is positive, is negative, is positive, sorry. If the most significant bit is a 1, the number is a negative. And this is the thing here, right? The most significant bit is a marker for both sign magnitude and 1's complement. So this must sink in here. If I tell you I have a number, 1, 1, 1, 1, 1, using sign magnitude, is this number positive or negative?
It's negative.
Right, exactly. So I hope I've answered your question. The person who was asking, is it important to put a 0? For sign magnitude, yes. Although, listen, I mean, you will soon discover that computers typically use 2's complement to represent numbers. So this was used many, many years ago, right? It's no longer there, but it's just used as a tool to help you understand exactly how a computer performs calculations. To put it out there that there are other techniques that people have come up with. Techniques that work just as well, but they have certain flaws, right? All right. This is getting fun, right? So here's the thing here, right? Let's say we are using 4-bit representation, and we want to represent certain numbers here, right? And I'm wondering why we want to represent certain numbers. Using 4-bit representation, you notice that we can easily compute. We can easily compute the values and the corresponding signs. We know that if the leftmost bit or the most significant bit is for the sign, right, which is here, we know that all of these are going to be zeros, and then the remaining bits are going to represent the value, right? There's something else that I hope I mentioned this, but if I don't, I'm just going to say it right now. There's something else that you will notice, a flaw with sign magnitude and in fact 1's complement. The fact that the maximum number, the maximum value that you can use to represent values using sign magnitude and 1's complement is much, much smaller, right? So in this case, using 4-bit representation, the maximum positive number that we can represent is 7. Why? Because this leftmost bit, the most significant bit, is always going to be a 0 to represent the sign. And so the maximum we have is a 1, 1, 1. What is 1, 1, 1? 1 plus 2 plus 4, right, which is a 7. But if this was an unsigned integer, the maximum number that we would use to represent the value would be a 1, a 1, a 1, and a 1. And this is an important point that should sink in, right? The fact that when you're working with computers, the value you're representing is something that's extremely important, right? So this would be 1 plus 2 plus 4 plus 8, which is slightly larger actually, right? Is this making sense? The number here would be 15 and not 7. I don't know if people are following through here, but so here's the thing: representing negative values, yeah, would be like so. We are saying we get the magnitude is going to be the same still. The only difference is the most significant bit or the leftmost bit, which is going to be a 1 for these negative numbers. Now, I did mention that I was going to cut this class short, but I want to leave you with this thought here, right? It's almost 6:40 and I'm rushing for a meeting on campus. But I want to cut this short here and just give you a scenario. If we are saying, please follow through with this. If we are saying that this is how we are representing numbers, right? Both positive numbers and negative numbers. I want us to do a simple experiment and take this case here where we have 1. Are you following?
Yes.
Yes, sir.
We're going to get 1, right? -1 is 1001. Negative, oh crap. -1, sorry about that. -1 is, oh, by the way, I met some people yesterday. It's not like I was ignoring you. I was rushing somewhere and then there was someone else who was there. I saw you, but I said hi, right? I'm sorry that I didn't stop. I could have stopped, but I was rushing for another class. I think, yes, I was. I'm sorry, I didn't. I think it was Maui and company or something. It was the company of Oh, it was Leander. It was nice to see you on campus. Right, so look at this, observe. +1 is 0, 0, 0, 0, yeah, is using 4-bit representation here. 0, 0, 0, 1. Yeah? -1 is 1, 0, 0, 1. Now think about this for a second, right? If we are saying that this is +1 and -1, what is +1 plus -1?
0.
Beautiful, 0, right? If we are saying this is 0, using the rules that we looked at, it's 0 using binary addition, right? And by the way, a computer doesn't have a subtractor, right? There's no hardware component that does subtraction. It's the same adder that does your subtraction, because when you are adding, if you want to subtract, you can add the numbers by just assuming, by just reminding yourself that the minus is just, it's a negative number. You can either add 2 negative numbers or you add a positive number and a negative number. So there's nothing, you don't need a hardware component that's going to do subtraction for you, because the same component that does addition for you is going to do subtraction for you. Do you understand? So in this case, we're saying if we add +1 plus -1, we're supposed to get 0. But look at what happens when we add these numbers. Let's add. What is 1 plus 1? It's 0, carry and result. 1 and 1 gives us 1. We have the 0 result, right? Sorry, 1 here, right? 0, 0, 1 gives us 1, right? Are you following?
Yes, sir.
Yes, sir.
0 and 0 gives you 0. 0 and 1 gives you 1. Now, if you were to convert this, right? Now, it doesn't matter whether, because you're using sign magnitude here, you sit there and just say, well, the leftmost bit or the most significant bit is a sign. That's fine. It's negative, right? But ask yourself this question. What is 0, 1, 1? It's 2, right? Did you understand what's happening here? What is this value here? 0, 1, 0.
Yes, sir.
Yes, sir. It's a 2.
It's 2.
Yes, it's 2.
It's 2, meaning that the answer you get when you try to subtract, when you try to add +1 and -1 using sign magnitude, you get -2. It's wrong. It's not correct. This is one of the flaws. Now, you can sit there, the smart people that have designed hardware components in the past, there are workarounds for this, but what we're just trying to showcase here is that the result that you get don't make sense, right? And you can actually try and play around with all these numbers here and try and see if you'll be able to get the correct answer. In certain instances, you might be able to get the correct answers, but there are certain situations where you don't. Worse still, the other part that I mentioned, the fact that you have a -0 and a +0. This makes no sense. Why would you want to have a -0 and a +0, right? Just wasting space here. So guys, I'm going to see you tomorrow, right? Where we start our discussion of 1's complement. I will let you sleep over this. And there's another example here that you can go through. If you want, tomorrow we can just start by doing a recap and look at positive 5 and -5 and see if we can compute the result. And you notice that we won't be able to get what we want here. I'll see you when you see me. I'm signing out now. Thanks a lot.
Thank you, sir.
Quiz on Tuesday. Bye.
Yes, sir.
It's on Tuesday. Bro, and guys.
I mean, guys, yeah, 1020. What's going on? Has he announced? Quiz.
Kaya but I read some kind of quiz, so but things are going on here.
It's too close to the end. Writing physical exams.
Guy, imagine service, eh?
They're easy. You just need to take time. Solving them. Once you become good with this, to become like muscle memory, like you said, and it's right.
Yeah.
It's just that this quiz that we wrote, we just blotched it up, most of us, because of our stupidity.
Have you landed? Or maybe.
Yes. And bye. You fight.